Biology of Fishes, the 25th of October, 2012. Moving on, the exam report in flash form is up, as I explained in my email sent out to all hands, including our audit folks who are sort of monitoring the courses as ghosts, I guess you could say. So they have access to that, so they can see how it went. Ray's not too. He's pretty much here in the flesh, so he knows what's going on. But anyhow, I encourage you to download that file and play it back if you want to see the way I thought through the exam. Right after this session today, I'm hoping that some of the people who are registered as on-campus distance students might drop by and we can go over the exams together, the personal, their own exams. Last time I talked about heat transfer and body temperature, and I ended the session sort of talking about what I call thermal runaway. And it didn't work as good as it should have, so I decided to invest a little more effort and come back to you again today because I think it makes some good points that you ought to come away with. This is basically the model that I showed you, the Stella model for thermal runaway. And what I was explaining was my overstatement about exponential processes quickly getting out of control and going to infinity, basically. In this case, we're talking temperature as a consequence of the Arrhenius effect on resource processing, metabolism. And I put in the values that you reported from Lab 2 as far as the intercept oxygen uptake rate at 0 degrees, and the value of Q for the rate coefficient that you put in, that you got out of your lab. And so what we got here is a system where the temperature starts off at 20 degrees, and the temperature affects the metabolic rate of this system, this fish, this ecofish, in an exponential way, and that then leads to the next increment of heat production, which feeds into the system raising its temperature, because I'm converting heat into an effective temperature change in the absence of any loss. Except that I've now have a provision here for loss, and the loss follows heat transfer dynamics, just like Newton's law said it should, where it's the difference between ambient temperature and body temperature at that moment, multiplied times some rate constant, KHE in inverse minutes, which is the one I've got, and I'm using basically the one that you reported, or I will at least. Right now I've got a 0 in there so I got a system where I don't have any loss, right? I'm trying to repeat what I did before. Is everybody with me on that? So right now we got a 0 there, so this is guaranteed to be 0 because we're multiplying, whatever that difference is, it's going to be multiplied by 0. So we're not going to have any outflow of heat from this system. It's going to be just like it was before. And go back and run it again, and I think I set it up this time to run with, I'm only running at 50 hours. That was plenty to see what was going to happen. And I'm using a 100th of an hour step. And when you do that, you get the same result we got before. It runs away. This number, the value becomes too large to represent. That's what's causing this. If there's no limitation of any kind. And I pointed at the time, my comment about getting to the temperature of the center of the sun is not outrageous as long as you don't consider the fact that it takes some sort of resource to power that reaction, and you're going to burn all that up pretty quick. But just forget about that. And instead, think about the other side of the issue here. the other side of the second law of thermodynamics, I guess. What goes up has to come down, and inputs got to be equal to outputs. And so I put a loss term on here, and I'm going to put in place of the 0, I'm going to put what you got, which is about 5/10 of an inverse minute for the rate constant for your 20-gram ecofish. And as soon as I do that, the picture changes pretty drastically. There's the old picture. Here's the new picture. And what you got to notice here is the rescaling that's going on. Notice now we're starting at 20. And within just a matter of a few hundredths of an hour, a few tens of hundreds perhaps, we have reached an asymptotic relationship here where, recall what I said, and the reason I'm going through all of this rigmarole now is just to emphasize the point that body temperature reflects the balance point between the rate of production of heat and inputs and outputs loss. And so the loss rate is driven by the differential between the existing temperature in the body and the outside world. And as soon as that difference gets to be at all large, any value of K is going to be enough to cause that output to be great compared to the input. And so now everything is sort of balanced, and we got a stable system. And it goes on forever, with only what we said in lab was right, a few hundredths of a degree excess. I wanted you to all have access to this little simple-minded Stella model that is easy to understand, easy to see every piece. It's basically what's running inside of Ecofish. And I wanted you to also be able to compare it with the equivalent Excel model. And so I put up both of those. This other one here, if you hover over that link, you'll see that that's the XLS equivalent. And it's exactly the same model. And I've got it downloaded already. It's going to force me to open it in Excel 2010, which I'm not going to do. I'll get it this way. Microsoft, unless somebody can show me how to do this, once you've got the newer version of something that Microsoft is promoting, like Windows, or like Office or Excel or a piece of Office, it's almost impossible to let it even show you the old version. You can't even get it to open with, and you can search and it won't show you. So I don't know. With somebody else's program, it'll search and show it and find the program for you to use. But okay, so that's another complaint here. We've had a complaint session already before I started recording this morning. All right, so there's exactly the same model, and I wanted you to be able to see. Let's see if I can view that dude with a little less resolution here, like down to about 50%, so you can see it all. Well, you can nearly see it all. So here's the same model in Excel. This is what it takes to do the same exact things in Excel. Each one of these. So that's just counting up at 100th of an hour in time. Here's the calculation you need to do to get VO2, and then here's the calculation you need to do to get heat out of that, and then here's the calculation you need to do to get heat loss out of that. So, in other words, I'm going through the same exact math in Excel with the same time step as I went through in Stella, just so you can see side by side how the two work. You're probably more familiar with Excel. I'm trying to get you to like Stella, because I think Stella is logically a little easier to get a grip on how it's doing things. So I've got this set up with exactly the same, so I got it set up with 0 for the rate constant as it comes out of the box as I put it. Let me go back to a little bit higher resolution, or lower resolution here. Zoom to, say, 75%. make it a little easier to see. Okay, so I've got the K value set to 0, so we got no loss in this version. As soon as I put in 0.05 inverse minutes, then when I hit the return, what's the graph here? It's also scaling automatically, just like it was with Stella. Well, I say it is, and probably I said wrong. Yeah, I said wrong. It's not rescaling. It doesn't do that. So we're going to make it scale from 0 to, instead of 4,000, we're going to scale from 0. No, we're going to scale from, just like Stella is scaling from 20 to, let's say, 21. That's not what it's doing, but we'll... All I want to do is just show you that you're getting exactly the same result there. In fact, you can see it here. Maybe that would have been enough just to show you the column of, here are the column of TB values, and I'm scrolling all the way down, and I'm all the way down here to 50, and it's 20.04. So, anyhow, I wanted to leave the story complete, even at the risk of overkill, as usual. All right. These little models are there in case anybody wants to fiddle with them. Do I have any questions from my local group about any of that? So temperature may go to the center of the sun if there's an infinite amount of energy, resource available to power that reaction, right? And you've got a closed system. Let me talk about the next topic, acclimation and acclimatization. What I want to do is start the process of sort of considering with you in a formal kind of way adaptations that fish and other animals make on an individual basis over reasonably short periods of time that are reversible for the most part. And the labels that are used to describe these kinds of adaptations, I think the best labels, yep. Oops, I've got it. Allison points out that you don't have the handout, but I've got it here available for you. I just didn't hand it out. So I'm passing out the 3-slide per page here in the room, and that's going to be available to people that want to download it at a distance or who aren't here today. Let's start you over here. Just ask you to pass those around. Thank you. So, let me tell you what I'm not talking about. I'm not talking about genetic adaptation, selection for a certain subset of genetic material that tends to then perpetuate itself through time, subject to, of course, changes that occur due to things like mutation or even reassortment. I'm not talking about the kind of changes that persist through the lifetime of the whole individual that are genetic in their basis, that have to do with the fact that that particular animal has a different genetic constitution from another animal of the same species. And I'm not even talking about what has been called irreversible non-genetic adaptation by Otto Kinney many years ago, in which the organism's physiology is in some sense fixed early in development, and that fixed condition persists in through the lifetime of the individual. I'm not talking about phenotypic plasticity even. What I'm talking about are compensatory physiological changes in response to change in the complex of environmental factors or in response to a single environmental factor under usually laboratory conditions, because it's hard to control just one factor in nature. So these are processes that have been labeled acclimatization in the case of the response of the organism to the whole suite of environmental factors, usually in nature, or acclimation, compensatory physiological changes in response to a single factor. And then there's another word that sometimes is misused and confused with that acclimation. That's got to do with politics and debate. It's agreement with unanimous consent. That's with two A's here. So that's not the word. The word that we're looking for is acclimation with an I in this position. I think I have a piece of Charles Warren's book up as a PDF down in the reading list. I'll have to see if I can bring that up and insert it if I didn't, because I don't want to refer you to anything that I know you won't be able to get your hands on very easily, and you probably wouldn't be able to get your hands on that book anymore. It's out of print. I need somebody to remind me if they don't see this and if they'd like to put this chapter up. Within acclimation or acclimatization, there are two subsets that I'd like to consider with you. One of these has to do with change in the organism's ability to perform work over the tolerable zone of some factor or set of factors, whereas the other has to do with the change in resistance to lethal effects of environment at the extremes of some factor or factors. So here's the formal definition that I would offer. Capacity acclimation is compensatory physiological change in the ability to do physiological work in response to the change in some single factor, usually again under laboratory conditions. And resistance then is change in the ability to resist death at extremes of some factor. So it's pretty obvious that capacity has to do with performance. If you want to think of a pair of words, think of capacity and performance, and think of resistance and lethal or death. So here's a old rough drawing illustrating acclimatization. And both capacity and resistance are suggested by this graph. You know, here on the y-axis is some rate process, like something like bioenergetic components like consumption rate of feed or respiration rate or growth rate. And on the x-axis is some factor to which the animal is acclimated acclimated either in the context of a laboratory acclimation process or a field acclimatization situation. And I guess what I'm trying to illustrate here is you know, you go out, you take samples of fish from a pond in the wintertime, and then take them into the lab and test them for one of these Y responses at different levels of temperature. And what you might get is sort of an Arrhenius effect again, but it doesn't go on forever. You know, like it doesn't go to the center of the sun. What it goes to is right there, and then there's an abrupt crash in the performance as the animals reach the lethal limit. And if you do the same thing with the same species in the same pond in the summertime, you'd probably get a different pattern that would be shifted. The shift reflecting acclimatization. And so in the summer, you know, the whole curve is shifted to the right, and the ends of the distribution here, which suggests a lethal endpoint. In other words, the idea is that you don't get any values below that temperature for winter acclimatized fish because they don't live long enough if you try to test them below that temperature to give you results. And similarly, they don't live long enough to give you results if you try to test them higher than that temperature in the winter. But in the summer, They don't live as well at low temperatures. In other words, it takes a higher temperature for them to minimally survive. But they do a lot better at extreme high temperature. So the difference in the positions of these two curves here reflect this performance difference that we call capacity acclimation, or in this case, acclimatization, I guess. The difference in the endpoints of the two curves reflect resistance differences. And if it turns out that performance is the same for summer acclimatized fish at the typical summer temperature as performance in the winter acclimatized fish at the typical winter temperature, notice this straight across line here, then we say that capacity acclimatization is perfect. The word that's used is perfect, and I'll have more to say, maybe more a better illustration here. So this is the same graph, except now I've taken logarithms to straighten out those exponential increases. And I'm talking now about a laboratory situation in its entirety, where the different exposures that the animals have prior to testing are accomplished in the lab at controlled levels of temperature with everything else constant. And then they're tested in that same lab at various temperatures with the same, and the other conditions all still remaining constant. So we would change the label there from acclimatization to acclimation. Say now these animals are acclimated to two different temperatures, T1 and T2. And then they're tested at a whole variety of temperatures, all the temperatures over which we can measure responses. And the extreme values are indicated by the ends of the line. So again, we see the evidence here of resistance acclimation going on. Fish that are acclimated to a higher temperature have a higher lower lethal temperature and a higher upper lethal temperature. In this case, notice that acclimation at T2 and then testing at T2 gives a somewhat greater rate of response than acclimation at T1 and testing at T1. So in this case, the acclimation or the compensation is said to be partial and not perfect. And I should have made that one look just like the other one, so it start off with perfect and then go to partial, but I didn't. And I didn't want to change it at this point in the game. So, but notice the dashed line has a positive slope here in the case of partial compensation. There's the case for perfect compensation. I should have put that one first, where the line has a horizontal position. In other words, the slope is 0. So now, T2 acclimated fish perform at T2 just exactly at the same level as T1 acclimated fish perform at T1. So it's said that compensation is perfect. These labels, perfect, partial, and the others I'll give you in a moment, all have to do with performance and capacity acclimation. Suppose we did the same experiment again, except now using a different species of fish or a different environmental factor. There's no difference between fish that are acclimated at T1 and T2. In other words, we can't tell what their acclimation was by their response. We put them in the test environments, and it's like we're just taking them all from the same group. That is, T1 acclimated fish perform at every temperature where they're tested the same exact way as T2 acclimated fish. The case here would be no compensation. What I'm doing is I'm building the set of all possible degrees of compensation. And I started with perfect, and I talked about partial, and now I'm talking about none. No compensation. Here's a case that's really strange where if you're acclimated at the higher of the two temperatures, you actually don't perform as well at that temperature as animals acclimated at the lower temperature perform at the lower temperature. Notice the slope is now negative. And this would be a case that would be labeled overcompensation. The over part may not make intuitive sense until you consider the dynamic relationships, but I'm going to show you those in a moment. Right now I'm showing you steady state. In other words, animals that are fully adapted at T2 and then tested instantaneously at all the temperatures where they can be kept alive long enough to give a result. Give this line. And then animals that are fully at steady state at T1 are tested at all the temperatures, and these are the instantaneous responses. And that line has a negative slope. Here's another case, and this one's called overcompensation. And let me back up one notch here. Notice that up to this point, all of my T1s are to the left of all my T2s for acclimation, and all of a sudden T2 has moved to the other side in this case. So this is called reverse compensation, where now animals that are acclimated to T1 perform at T1 at a level that's way down here compared to animals that are acclimated to T2 and tested at T2. Look at the line there. The line there is even steeper and positive than the unacclimated lines, the lines for the unacclimated case, where the animals are all acclimated to the same value and then tested, and you got instantaneous responses. That's what the values along this line are supposed to represent. So we call that reverse compensation. And I really like this to pull it all together, and I hope you will, a summary statement. Where now what I've got is an x-axis that is only that subset where the test temperature or the test condition is equal to the acclimated condition, the acclimated level of that factor. So test equals acclimation. So everything that's on this graph is designed to show what happens when the animal is tested at the same level to which it's acclimated. And if the line is flat, then we say it's perfect compensation. In other words, it doesn't matter what temperature you're acclimated to. When you're tested at that temperature, you have the same level of performance as for animals acclimated to some different value of temperature and tested at that temperature. Each group tested at its acclimation temperature performs at the same level. What would the Q10 be? Well, the Q10 is the measure of the ratio of the rates at two different temperatures 10 degrees apart. And in this case, the performance is the same at two temperatures 10 degrees apart, so it's a ratio of 1. And so the Q10 is 1. So we can measure this degree of compensation we can express it as the Q10. Q10 is 1. Let's go next to this case of no compensation. In the case of no compensation, remember everybody falls on the same line no matter what they're tested to. And I say that the Q10 is between 2 and 3 because I'm claiming that I start out with cases. Notice that all these lines have the same slope regardless of which degree of compensation. They're all intended to have the same slopes. And so if that's the case, then that's the slope. And the slope happens to be the typical slope, which is somewhere between 2 and 3. So that's the reason I give a range for that one. It could even be below 2. It might be 1.5. So anything between these two, we would say is partial. In other words, partial could approach perfect, or it could approach no compensation. And so if the Q10 is between 1, which is the case for perfect compensation, and the 2 or 3, which is no compensation, then we would claim it's partial. And of course, the reason there's a range up here to 2 or 3 is because there's a range here. If compensation is reverse, then the slope is even steeper than the case of no compensation, and so we'd say the Q10 is greater than whatever it is for no compensation. That is, greater than 2 or 3 or whatever is the proper value. And similarly here, for overcompensation, the slope is negative. That's the only case where you've got a negative slope. So there are 5 degrees of acclimatory compensation. And I would like it if you could all tell me back, how those 5 degrees work. I might not ask you to do all 5 of them, but you ought to be able to do that for yourself. Okay, you can think about this as sort of an aside, but it's an aside that's really important in understanding how nature works. This is from one of Warren's figures, and it's actually for, I think, rainbow trout. And what it's showing is that if you consider things that are forced to their maximum values rather than their voluntary or routine values, then optima become evident. And here what we got are rainbow trout, I think, or some salmonid that is acclimated to temperatures all the way from 5 degrees at the lower end to 25 degrees at the upper end. And tested then at the temperatures indicated on the x-axis for something like the logarithm of maximum performance rate being growth rate maybe food consumption rate. And, for each of the cases, the pattern looks, like what you'd expect. I mean, there's this more or less linear relationship over most of the thermal range, but then there's a maximum where things go to collapse, like here. And one of the things that Warren emphasizes is that, when you do these kinds of experiments, typically the optimum, or the value that is optimum, has this pattern. So for animals acclimated at 5 degrees, performance maximum occurs on the left side of this peak, and as the temperature increases, notice that this position shifts so that at 15 degrees, the optimum temperature for performance is nearly the same as the acclimation temperature. But then as you go even higher, over to this side, notice it shifted to the other side. So now a temperature of 20 degrees is actually inferior to a temperature of maybe 18 degrees if you're acclimated to 20. And by the time you're acclimated all the way over here near your ultimate lethal, upper lethal limit, the temperature that's optimum for performance is way lower than the temperature you're acclimated to. It might be down here. It's not maybe that it's so much lower, it's that performance is a lot greater at like 20, 22 degrees, 21 degrees. So this is the pattern that's sort of characteristic for maximum rates of performance. It clearly show evidence of optimum, both over the whole span of acclimation levels and within any span at a particular test temperature. Is everybody kind of with me here? That maximum performance for 5 degree acclimated animals is up here around 8 maybe. Maximum performance for 10 degree animals is not at 10 but somewhere up here around 13. 15 is 14. I should have drawn this so that 15 was right there at the peak, so that it was the global optimum. 20 degree acclimated, it performed better at 19 at a lower temperature on this side of the curve. So this dashed line is designed to show you the combinations of acclimation and test temperature that are optimum. This is probably what I'll put on the exam on the final. I'm not going to completely guarantee it, but I'm probably going to do that. So here's a comparison of situations where there is clear evidence of resistance acclimation, but no capacity acclimation on the left. Why do I say that? Because these lines are supposed to be right on top of each other. I had to draw them a little offset so you could see there were different lines, but the intent is that they're right on top of each other. And yet their ends are at different places. So, you know, this group up here has a higher lethal level than this group down here, and has a higher lower lethal level as well than this group over here. But over the part of the thermal zone where they actually can both survive, they have exactly the same level of performance. So that's just I'm not sure there's any species that actually achieves that. But that would be the logical, be one of the four possible situations. Here's another possible situation where it's just the opposite. There is evidence here clearly of a capacity difference in acclimation, but no evidence of any resistance acclimation. Why is there no evidence of resistance acclimation? Because the endpoints here are exactly in the same places for both acclimation states, both upper and lower. So, if I ask you to, show me the other two cases, could you do that? What would the other two cases be? Here it's yes resistance, no capacity. Here it's no resistance, yes capacity. What about yes resistance, yes capacity? And what about no resistance, no capacity? Well, you go back and look at those other drawings that I did a little earlier, and it should become clear. So if I ask you to do the case of capacity and resistance, then you draw me two lines that have different endpoints but are offset from one another, like these two are, except with endpoints in different places. And then if I ask you to draw me the case of no resistance, no capacity, you just draw me two lines that are one right on top of the other, having their ends at the same places, right? If that doesn't sound completely sensible to you, then and you can't make it make sense, get in touch with me. Anybody here do you think you could draw me four graphs that would do this job? Okay, so another set of ideas, a little bit complicated, but not too bad once you dig into it. This is a classic graph that's called a lethal temperature resistance pattern graph. And what it's intended to show is the lethal temperature resistance patterns for a representative fish. In this case, I'm thinking about a bluegill. Over the entire spectrum of temperatures to which it can be acclimated, and then for each of the temperatures at which you might do a step change test. In other words, take it from the acclimation state, once it's fully adapted, as fully as it's ever going to be at that temperature, and then step it to a new temperature, either higher or lower, and hold it indefinitely long and measure the time it resists death. That's what's intended here by this graph. On this axis is test temperature, and notice this is another one of those cases where X and Y are reversed from what you'd expect, because the independent variable is the temperature at which you're testing, and the response is the resistance time that you're getting. Notice something else, that temperature is on a linear scale from 0 degrees down at the bottom to 45 at the top. And resistance time is on a log scale, reflecting the fact that the distribution of mortality, as I told you in lab 3, I guess it was, typically is log normal. The log normality of that is indicated by this one little distribution that I've drawn up here, where what I've intended to show is the frequency of resistance times recorded for a test done at about 43 degrees here for a group of fish acclimated to 35 degrees. And the whole idea is that if the distribution of mortality is log normal, then that frequency distribution will have a normal shape when you plot it on temperature log resistance time axes. In fact, we might expect that each of these points around here along the line would have the same shape distribution with about the same variance if everything was nicely controlled. That's not really true, but that would be the ideal situation. So help me interpret this. You know, what we're saying is we got this fish and we're going to acclimate it to all temperatures over which it can be acclimated, and we discover that no matter how gradually we approach 36 degrees, our fish die at 35. And no matter how gradually, well, I guess at the bottom end, we go down to the freezing point and they're still there, but then they can't swim around in ice, so they're going to die at the freezing point, this freshwater fish. So the ultimate lower lethal temperatures are truncated by the freezing point of water, but the ultimate upper lethal temperatures are just fixed by the physiology of the particular species. In the case of centrarchids and a lot of freshwater fishes of the temperate zone, that upper lethal limit would be around 35. So we can acclimate fish to 25, we can acclimate them to 15, to 5, and to 0 if they're bluegill, for example. Can't acclimate them to -1 because they're in ice. Can't acclimate them above 35 because no matter how gradually we try to move them above 35, they die on us. So that's the spectrum. That's the zone of temperature over which they can be acclimated. So we now do tests by step changes from the acclimation temperature to the lethal, just like you did in Lab 3 in a virtual sense, except you were using ammonia and copper instead of temperature. So when we take fish acclimated to 35 and we step them to 45, they die in a minute. The median fish is dead in 1 minute. When we step them to, let's say 40 out here, the median fish is dead in about 100 minutes, a little over. When we step them out here to 36 degrees, the median fish is dead in about 9,000 minutes. When we put them at 35, the median fish doesn't die because it's already at 35, right? It wouldn't be acclimated. It wouldn't be there if it was going to die there, or the median one is not dying. So these resistance lines tend to break away to infinity as you reach these endpoints that I've indicated here. These are called incipient lethal temperatures. In the case of 35 degrees, that's both the incipient lethal temperature for 35-degree acclimated fish, and it is the ultimate upper lethal temperature for this species because that's the highest temperature it can be acclimated to. And notice that that turned out to be about 10,000 minutes, about a week. 1 week is about 10,000 minutes. And I think I made that case when we talked in Lab 3 about how this 10,000 1 minute, 1 week time period tends to be special for some reason, probably having to do with molecular biology that I don't understand. Let's consider the other extreme. We got 35-degree fish. We move them to a lower temperature by stepwise fashion. If we move them down to 20 degrees, we don't get any mortality. They like that just fine. Move them down to 16 degrees, we get less than the median fish dead at least. But as soon as we go to 15 degrees, the median fish dies for a 35-degree acclimation set at about 1,000 minutes. And then as we go even lower to 10 degrees, they die in 100 minutes. At 5 degrees, about 12 minutes. These are all hypothetical, obviously. So that's the situation for 35-degree acclimated fish, fish that are acclimated to the maximum possible temperature. What about when they're acclimated to the minimum possible temperature, which is 0? Well, 0 fish can't be killed at temperatures below 0, without being frozen solid, so that's irrelevant. In fact, none of the temperatures from 0 up to about 23 degrees result in a median lethal fish, or the median fish being dead in a finite time. But as soon as we go a little above 22 degrees, in fact it looks like 22 and a half, then we get the median mortality at about 100 minutes. And then as the temperature goes even higher, the resistance time gets shorter. And finally, when we get down to up here to, say, 28 degrees or 29, we got almost immediate death. In between, the lines are in between. They tend to be parallel within the upper resistance pattern distribution and within the lower, but the lines for the upper and lower patterns tend to have different slopes, and the spacing between them then tends to be greater. In other words, it looks like 1 degree is a lot more important for high temperature than it is for low temperature. Look how much further it is from the 25 to the 35 degree line here than it is up here. So what about these ends out here? These endpoints we call the incipient lethal temperatures, and what they represent is the point of a tie, I think, between the accumulation of the damage being done by the extreme temperature and adaptation to that temperature, or recovery from damage that's already occurred. So what we're saying is that if you have 25 degree acclimated fish, a bluegill I'm thinking about, at all temperatures above 33 degrees, the median fish dies in a finite time, the time being something less than, it looks like, about 1,000 minutes. But as soon as you go below 33 and try to do a test at 32, the median fish just, sort of straightens up and flies right and recovers and lives on more or less indefinitely long. Maybe its lifetime is shortened, but the time is long relative to the scale of this graph, even with 100,000 minutes on it, which is 10 weeks. Same thing is true for 15 degree acclimated fish at 29. Above 29, they die in a finite time. Below 29, they live indefinitely long, the median. So we say that 29 is the incipient upper lethal temperature for 15 degree acclimated fish. And you can recognize these same incipients at the lower end. I didn't label it for some reason, but I can see that 35 degree acclimated fish, in other words, fish acclimated of this species to the highest possible temperature they can be acclimated to, to the ultimate upper lethal have as their incipient lower lethal about 15 degrees. So we'd say that the zone of tolerance for a 35 degree acclimated bluegill is all the way from 15 on the lower end to 35 on the upper end. Outside that zone, it's in what's called the zone of resistance. Let's see if we can identify the zones of tolerance and resistance for 25 degree acclimated fish of this species. Well, it looks like 5 degrees is the incipient lower lethal. And for the incipient upper lethal, it looks like 33. So I would say that the zone of tolerance is all the way from 5 to 33 for this 25 degree acclimated fish. And resistance is outside that region. So these resistance time patterns are the way the data are generated, and then the way they're used is in, I ask you to plot the incipient lethal temperatures on your own here. I'm going to do it for you, though, probably in the next slide. Do I do it for you? Yeah, I'll do it for you. Or at least I do it. I don't know if it's the same data, but suppose you make a plot where you plot the incipient lethals, both high and low, on this graph, and I'm going to do a little bit of that with you. I'm going to convert to Alt Z here. You're going to have to look back at your data there from your handout to tell me what the values are, because I can't look back and see them now, right? So let me ask Volimar what the incipient upper lethal temperature is for a fish acclimated of this species to the lowest temperature it can be acclimated to, which is 0. So what is the incipient upper lethal temperature for a 0 acclimated fish? It's written on there, isn't it? Is it not legible on your little? I think it's 22 and a half, isn't it? For 20. Well, I think it's actually written. I kind of got it memorized at 20. Okay, so we can put a value right there. We can plot the incipient upper lethal temperature for a 0 acclimated fish of our hypothetical species right there. Okay, what about if it's acclimated to 5? You probably can't read it. Squint your eyes and guess for me. 25? Okay, good deal. So I'm going to put a point about there. Let's see, what have I got? I don't have 10 showing. I got 15 though, right?
29.
About 29? Okay, so there's the 15 degree acclimated fish at 29, and then 25 is 33, right? You can see I'm kind of struggling here because I don't have any grid lines on my graph to work from. All right, but then something funny happens as we going up to, well, first of all, 35 I know is at 35, right? Because that point's going to be guaranteed to be on the 1-to-1 line. And the thing I noticed that's kind of strange is this, well, first of all, this line here, if we'd have drawn it right, should be almost straight from here to here. But then somewhere up in here, it breaks over and is flat. In other words, once you are acclimated to a temperature above about 27 or so, there's no additional increase in the incipient. It's 35. Okay, we can do the same thing down here. What about 35 degree? What's the lowest temperature? What's the incipient lower lethal for 35 degree fish? 15. Okay, so I'm going to put a point at 15. And then at 25, I think it's 5. Okay. And then it sort of goes below 0, doesn't it? At about, 15 degree fish don't show up. You can't kill a 15 degree fish with cold without freezing it solid. And so it's kind of dropping below the freezing point. So it just kind of dead ends here, right? Truncated by I probably should have changed the color. So you end up with a shape, and I'm going to make the ends of I'm going to mark the points of the ultimate upper lethal here vertically, this line, and then the ultimate lower lethal is the freezing point of water, so that's kind of a phony line. And then here's the freezing point. So we end up with this figure, this figure here that we call a thermal tolerance polygon. And that's why it's called a polygon, is because it usually has a polygonal shape. In this case, it's got 1, 2, 3, 4, 5, 6 sides. Sometimes there are only 4 sides. How would you get only 4 sides? Well, you might have a fish that has a polygon that looks like this. And I should have made this a different color, probably. In other words, this would be a tropical form, a stenotherm, or not a tropical. It would be a cold stenotherm, wouldn't it? Because but it doesn't tolerate temperatures below 10 degrees. It can't be acclimated below 10. It can't be acclimated above 27. And these lines are supposed to be straight. Beg your pardon for my wavy hand, but that's supposed to be a straight line from there. Anyhow, so these are called thermal tolerance polygons. Inside the polygon is the zone of tolerance. Outside the polygon is the zone of resistance. There's an upper zone of resistance, or heat resistance, and cold resistance on the lower. So up here would be the zone of heat resistance, and down here would be the zone of cold resistance. So these things are kind of handy in that they define the set of all combinations of transfers that you could do that you would expect to yield a median survival, a median fish surviving indefinitely long. So if you start out with a fish acclimated to 25 and you move it to 25, obviously it's going to survive. Well, that'd be right here, wouldn't it, on the line. So you should be able to tell me for any acclimation transfer combination whether you'd expect the median animal to survive that transfer or not to survive. Resistance times get shorter as you get away from the polygon. In other words, as you move from the zone of tolerance to the zone of resistance, at first resistance is almost infinite or indefinitely long, but then the further you move away from the polygon, the shorter the expected resistance time. The more abrupt, the more extreme the transfer. So let me get out of that, and I wanted you to do that kind of on your own, but I guess suffering along with me is almost the same thing. I want to stop drawing and go to my Alt-Z. Okay, so I think there is the polygon for the data that I just showed you, the carefully drawn polygon. And this thing is called Fry's temperature tolerance polygon. It provides an explicit measure of eurythermality. You should maybe have been thinking already, hey, the x-axis got degrees on it, the y-axis got degrees on it, so that means the area can be represented as squared degrees. And so squared degrees might be a proper measure for eurythermality. The smaller the number, the scalar part, the lesser, the more stenothermal the animal. So here's some actual values that folks have calculated from doing these step transfers to different temperatures like I talked about. For salmonids, the thermal tolerance polygon has an area between 400 and 500 squared degrees. For cool stenotherms like yellow perch and some of the northern minnows, 700 to 800. Southern minnows, 800 to 1,000. Gambusia bullheads, 1,000 to 1,200. Goldfish is, I think, still the published record holder, and that's 1,220, but I think some of the tilapias and maybe some of the sopranodons might outdo it. They just don't have the tolerance on the low end, though. Typically, tilapia species are usually going to have a lower lethal, an ultimate lower lethal. Now you know all the jargon. The ultimate lower lethal of most tilapia species is going to be in the middle single digits to upper single digits, 5 to 10 to 11 degrees, somewhere in there. Goldfish are 0 on the lower end. They can handle a step to 0 if they're acclimated low enough. And they can acclimate to 0. So, other folks have pointed out in the context of Fry's thermal tolerance polygon that performance in general, not just survival, tends to be indicated by the position of the thermal tolerance polygon. And you can do isopleths, for example, for maximum performance or performance measured like maximum swimming speeds. And the peak of the mountain for performance here typically is on the 1-to-1 line or pretty near it, and usually toward the upper end of the polygon. So here what we're saying is that for this hypothetical fish, we'd get 7/10 of the maximum performance possible anywhere within this sort of oval shape, and 8/10 here and 9/10 here, and the maximum would be right there at the tip of my pointer. That'd be the best possible combination of acclimation and test for performance. When you look at the actual data, there tends to be a ridge that sort of runs at a flatter slope than the 1-to-1 line. So for each level of acclimation, the performance occurs along a line that is that intersects the 1-to-1 line and has a flatter slope. So what we're saying is that we're saying the same thing that graph showed that I was trying to show with for rainbow trout, where I was talking about maximum performance as a function of acclimation and temperature for combination. I had 5 different acclimation temperatures, and then I was showing the performance rates at different test temperatures. And what we're saying is that when fish are acclimated to a relatively high temperature, above, say in this case, about 25 or so degrees, performance usually is maximum at some lower temperature, below the acclimation temperature. So at the tip of my pointer there, what we're saying is that if you're acclimated at 30 degrees, you might be able to perform best at maybe 26 degrees. And then as you come along the line, when you're acclimated to 25, you're best able to perform at 25. So 25 is sort of the global maximum. And then as you go even lower, if you're acclimated to 15, you probably perform best at maybe 21. And if you're acclimated all the way down here at 5, you're probably performing best at 15 or 10, something like that. So have you seen anything else that looks like that? Well, you know, no, you haven't seen it yet, but you will in Lab 5. It turns out that the preferred temperature relationship that fish exhibit follows this same ridge. In other words, fish tend to prefer temperatures where they can perform at maximum rates. So if you acclimate this hypothetical fish to 5, it's probably going to prefer something like 8:15. If you acclimate it to 15, it's going to prefer 17. But if you acclimate it up here at 25, it prefers 25. And you'll find out when we do Lab 5 that's why we call that the final temperature preferendum. The temperature where the final temperature preferendum is that temperature that fish prefer when they're acclimated to that temperature. If they are acclimated to a higher temperature, then they prefer a lower temperature. Trying to prefer something closer to where they do best, maybe, each time when they have a choice. And I think fish are doing that in nature all the time. They're always optimizing, moving with gradients. But I will talk a lot more about the distribution part of this. So that's a cleaner view of Fry's tolerance polygon. And you know what, I think I'm going to stop right here before I get into the dynamics of acclimation. I've just talked steady state up to this point, basically, and then I want to talk about the transient state part of it next time, but I don't want to start this without being able to finish it today. I don't want to keep you late. So we're going to quit right here and pick it up next Tuesday. And next Tuesday we'll also do Lab 5. And that's the last, for undergraduates, that's the last lab where you actually have to follow through with an analysis and do a report. In fact, it's the last lab anybody has to follow through and do an analysis and a report on. But the graduate students need to be moving ahead to about their own individual project work that they're going to do. Okay, well, we'll shut her down at this point.